Hi everybody! Today we're going to be starting our official introduction to calculus. Although technically we've already worked with calculus quite a bit previously. All of the work that we did with series, that's all second half of the year BC calculus, technically second half of the year calculus 2 if you thought it was difficult. Just doesn't require a whole lot of calculus to be able to do the problems though. So we probably already know 2/3 of the things we need to be able to do with series for those of you who've been able to pull everything together. And yeah, we'll need to add some things on, but we'll have a really good foundation for that when we get to that toward the end of the year in calculus. We're going to be kind of rolling backwards though and starting the official calculus course. If I had it to do over again, I probably would have issued everybody a calculus book as we were leaving on what apparently turned out to be our last day. I kind of thought we'd be back by maybe late April or early May, and so I didn't give everybody a calculus book. But usually we do a chapter or two at the end of the year, and normally I just go ahead and issue everybody a book. A little bit of background about the book we're going to be working from. We're going to be working from Paul Forrester's calculus book. Paul Forrester is I think he's retired now, but a former math teacher who taught in Texas for, 40 or 50 years. And he's known for having really brilliant and insightful application problems. He is wonderful at connecting calculus to all kinds of different areas. And as a result, his book has much more interesting problems than probably any other calculus book you're ever going to work with. And it's also a really nice tie-in with the AP exam because the AP exam is a problem-solving focus exam. And as a result, having lots of background in problem-solving is going to be really, really helpful for the AP exam. So anyway, I'll be making scans of the book. You don't have to worry about that. But I just wanted to give you a little bit of background about that. And when we switched over to the Forrester book years ago, our AP scores maybe doubled. I think the number of 4s and 5s we were getting went up by 2 or 3 times. So the book has had amazing impact on our calculus program. Anyway, I'm going to be giving you a little bit of an overview of what calculus is, okay? And a lot of you may not really have any idea what it is, other than just it's kind of the next math course after pre-calculus. So here's what calculus is. Calculus is actually the study of change, okay? Anything that changes can be described using calculus, okay? So really basic change, like something moving, a car driving on a highway, okay? Throwing a ball, that ball moves from one location to another. But basically anything that moves. We're gonna talk about a problem where a door is swinging open and closing, okay? We could look at money changing, the stock market increasing and decreasing, money in a savings account increasing with interest. We could talk about current events. We could talk about coronavirus, number of cases increasing, number of cases decreasing, that sort of thing. If it changes, it can be described using calculus. And so in a sense, you could really argue that calculus can describe almost everything in most fields. Okay, if you're working in medicine, if you're working in economics, maybe not used as much in a history course or something like that. But anyway, any kind of engineering, calculus is going to be all over the place. So really, really applicable. So then the follow-up question is, what's this going to look like for us? Well, we're going to be starting out in chapter 1, which is a really neat chapter. It's really unique. It's not in most calculus books. Chapter 1 is going to give you an overview of all of calculus. Specifically, we're going to make algebraic approximations of calculus concepts. The 2 big calculus concepts that we're going to focus on early are derivatives and integrals. And so we're going to talk about what are derivatives, how can we estimate derivatives, and also what are definite integrals, which is what we're going to be working with at the start here. And there are 4 little sections that kind of give us an overview. Once we have an idea of what calculus is, next year we'll be ready to start into actual calculus. So let's talk a little bit about this rate of change idea. If you think about rates of change, I want you to think about the different units, okay? For example, we might talk about something moving, and we talk about it moving at a certain number of miles per hour, or a certain number of units per second. If you buy products, say you buy a 12-pack of soft drinks, you might talk about spending, 25 cents per can, okay? Anytime you're talking about a rate, you're making a comparison between 2 different types of things, maybe a distance and a time, or a cost per can, that sort of thing, okay? Rates, or derivatives, as we're going to call them later, are always going to be comparing 2 units, okay? So I want to start off here with something that people would probably understand pretty simply. Imagine that you're going on a trip, okay? And imagine that you're out driving, and an hour into your trip, you're 100 miles away from home. And 3 hours into your trip, you're 200 miles away from home, okay? And if I ask you what your average rate was over the course of that trip, hopefully you could figure out the total distance and you could divide by the total time, okay? So in this particular case, you're starting at the point 1, 100, and you're ending at the point 3, 200, okay? And if I wanted to find the average rate, I'd find the total distance, I'd divide by the total time. The total distance here is going to be 200 minus 100. The total time would be 3 hours minus 1 hour, okay? And by the way, you can put your units in here too. This is in miles, okay? So we find that there was a total change of 100 miles in the course of 2 hours, okay? And of course, 100 divided by 2 is going to work out to be 50 miles per hour, okay? And notice something here. I was taking 1 unit and I was dividing by the second unit. And notice that the units of the final result match up with the units that I divided. I had miles on top and I had hours on the bottom. And so we end up having a unit of miles per hour, okay? Now, I want you to look at this calculation again, okay? If I take the point 1, 100 and the point 3, 200, what physical aspect of the graph did I just calculate when I took 200 over 100 and 3 minus 1? Okay, what did I just find? I actually found the slope, okay? The slope of this line is 50, okay? So if I have a distance and time graph, the rate of change, or the average rate of change in this case, which we'll talk more about moving forward, my rate of change is really just the slope of that line, okay? And what I've done here is technically calculus, but it's also technically Algebra 1. We just found the slope of a straight line, okay? Now, this is not a very realistic scenario, okay? In actuality, when you travel in a car, you don't always travel at the same pace, okay? This is assuming that you were going exactly 50 miles per hour for the entire trip, okay? And that's not really what the trip would look like, okay? Let's say you were starting out at a gas station here. Maybe you'd start out driving slowly and then you'd speed up, okay? And in actuality, you might do a lot of speeding up and slowing down. There might be a police officer and you slow down quite a lot. There might be a traffic jam and you actually stop. Chances are that your graph of your motion, this is having you start out very slowly and then kind of speed up, and you're still starting and ending in the same place. But anyway, what we're going to be looking at in calculus specifically is problems in which there's a lot of change, okay? So in this path that somebody's driving, it looks like they're driving slowly at first and then they kind of speed up, and by the end of the trip, they've gone 100 miles in 2 hours, okay? So I can still talk about the average rate of change, okay? The average rate of change here is actually what I already calculated. Okay, the average rate says, had I traveled at a constant pace, what would that rate have been? In other words, what would that slope have been? Okay, now, am I always traveling at exactly 50 miles per hour? No, okay, looks like I'm starting out very slowly here. Looks like I maybe speed up to even being faster than 50 miles per hour later, okay? What we're gonna be looking at in calculus is how to figure out what the slope is if you have a curve, okay? And so you can kind of see here, my curve is pretty level at the start, and it gets steeper, and it gets steeper, and it gets steeper, okay? The instantaneous rate of change is the rate of change at a particular instant in time. In other words, if I was driving down the highway and somebody took a photograph of me right here in my trip, how fast would I be traveling, okay? And the way we're going to be able to calculate that, you can actually draw the tangent line to a particular point, okay? And that tangent line might come through and look something like that. The slope of that tangent line to the curve there would be the rate of change at that particular moment in time. But that's going to be our challenge. When I have a curve that's changing, at some split second in time, what is my rate of change, okay? So anyway, if you look in a textbook, they're going to write this out using function notation. So you'll have some kind of a function, and to do this a little bit more generally, we'll say we start out at point A and we end at point B, okay? And so maybe I have a function that starts out very slowly and ends moving very quickly, okay? The average rate of change is just going to be the slope, and it's technically the slope of the secant segment going between these 2 points. We can say this is the point A, and then we can say the y-coordinate is whatever the functional value is at A f of A. We can say this is the point B, and the functional value at B. And so the average rate of change would just be the slope. And in algebra terms, you could think of this as a change in y over a change in x. In calculus terms, we tend to use function notation. So we could take the second y value and subtract the first. That would be f of b minus f of a. Okay? And on the bottom, we're going to subtract the 2 x coordinates. That's b minus a. Okay? So the average rate of change is really just a slope from a starting point to an ending point. It assumes that your change is happening at a constant pace. Okay? But if you had moved at a constant pace, that's how you can get to the same ending point from the beginning point as if you had started out slower and moved up more quickly. Okay? Now, meanwhile, the instantaneous rate of change, trying to find the slope right there at that point, or trying to find the slope right here at this point, or trying to find the slope right there at that point, that's going to be a little bit more challenging. Okay, finding the rate of change at a particular instant in time. And that's what we're going to be investigating in the first 2 sections. So that's a little bit of background. I'll go a little bit deeper in a couple of examples in the next video.